Okay, so welcome everyone. Welcome to the second meetup of the year of Deep Learning Sessions Portugal. Today, the meetup will be the host. Our guest today will be Ruben Branco, who is currently doing his PhD at the Faculty of Sciences of the University of Lisbon. His current research focuses on improving neurodegenerative diseases prognosis, specifically ALS and MS, using deep learning. But our meetup today is not about his current research topic, but about his work, the work that he has done regarding his master thesis, which is about a specific problem which is currently probably occurring on natural language processing, which is a problem of shortcut learning. He has developed a method, and he published a paper on the conference on empirical methods for natural language processing, where he received the Outstanding Paper Award for his work. And so I am very pleased to have him today as our guest. Just to provide a quick summary about how we work currently, the meetup will have 45 minutes of presentation by Ruben, and then we'll have something like 10 to 15 minutes of Q&A. So if you have any questions, you can put them on the YouTube chat, and we will answer them as soon as possible. Okay. So thank you for being here, and without further ado, I will pass to Ruben for him to do the presentation.
Okay, so welcome everyone. First of all, I want to thank the organization for inviting me to do this talk. So as Andreas said, I am a PhD student at the Faculty of Sciences, University of Lisbon, and I'm here to talk about shortcut learning in common sense reasoning and in NLP overall. This is work that I did during my master thesis, and it was a collaborative work, of course, with my supervisor, Professor António Branco, with João Silva and João Rodrigues, which you can see in the paper that was published in EMNLP. So to give you a bit of a background, I guess, just so we don't go straight into what we did in the paper, I wanted to give you a bit of a background on why we decided to do this. So this was work done during my master dissertation, which happened in 2020 to 2021. And I have been studying NLP since 2017 at the NLX group, which is a research group specific to NLP here in the faculty. You can see the website here, and you can even check this website here, which is you can find many tools on NLP and resources. So if you work in NLP, this is a great website to visit. So I started in 2017, and I had to, of course, learn a lot. It was during my first year of bachelor's, and it was in, I think, 2016 or 2017 when things started to really be involving into the neural part of NLP. So when deep learning really started to engulf the NLP methods. There was work done with deep learning, of course, before that, but it really started to kick off from 2015, 2016, 2017. And it was actually in 2017 when the transformer was released that the transformer really changed everything. So everyone started to use a transformer. It was the standard practice to really use it and to study it. And things like the GPT series were starting to come out, and we saw Bart and everything that came after that. And I remember having a lot of discussions at the time with my colleagues at the group, and as to, well, these models are getting really good. They're getting really good performance, really good metrics. So they are able to do a lot of tasks that previously were not that good with the previous methods. So what does that mean? Are the models getting really good, which means they're getting more intelligent, which means they're becoming more cognitive machines? And we used to discuss a lot about this, whether they really are intelligent or not. And then I think it was in 2019, if I'm not mistaken, a paper came out by Niven and Cao, and I started to discover a bit about this thing called shortcut learning. So in this paper, which I'm not going to go too much into detail here because I will talk about it in the next few slides, but in this paper, they took a data set from a task which is reasoning, so it has to do with argumentation. And they noticed that for Bart, for example, which was the best performing model, it was looking at specific words, like, for example, not or is. So specific words were actually very much correlated with the output, so with the answer that the model was supposed to give. And when they took out those words, or when they balanced the data set such that those words were not really that indicative of what the output should be, the scores came crashing down. So it went from, I think, 80 accuracy or whatever it was, all the way down to random baseline. And all of a sudden, something that seemed super good and that it was doing something that is, even for us, very difficult to do, it came crashing down, and it was basically a random classifier. And then more and more papers started to come out about this problem, and it seemed to be, I'm not going to say widespread in the sense that it happens in all tests in NLP, because NLP has been used for a long time. It comes all the way from the beginnings of AI, and it's been being used in the industry a lot. So I'm not going to say it's all in NLP, but it seems to be something that happens in some tests that we have discovered so far. But I've been talking about shortcut learning, but I did not mention or did not explain what it is. And there's this really good quote from the shortcut learning paper, which is by Garris et al., which was published in 2020, which says, shortcuts are decision rules that perform well on standard benchmarks, but fail to transfer to more challenging testing conditions, such as real-world scenarios. And if there's any of you watching that perhaps works in the industry and deploys machine learning models or deep learning models, perhaps this sounds like the problem of shifting the distribution of data, which is almost exactly that. So the model was trained on a distribution of data, and all of a sudden it goes into the real world where perhaps there's faulty sensors, or even the real world does not behave exactly like how it learned in the data set, and it cannot generalize to that, and it starts failing pretty badly. And we see this even in computer vision. So here's an example of that, where there's this model that was supposed to identify pneumonia from X-ray images. And in those X-ray images, the hospitals usually put a metal token that identifies the hospital, so that the person that is viewing the image can know, oh, this was, for example, from Santa Maria. Okay, this X-ray comes from Santa Maria. And instead of looking at the pathology in the lungs, so to identify pneumonia, the model was actually looking at the metal token to identify which hospital that image came from. And because there's different incidence rates of pneumonia across hospitals, and some hospitals have more pneumonia patients, other hospitals have less pneumonia patients, they could benefit from identifying the hospital, because in the hospitals that have more incidence rate, the model could just say, oh, this person has pneumonia. They don't even look at the lungs. Okay, this comes from this hospital, it has pneumonia. Or it comes from that hospital, okay, it does not have pneumonia. So it did not learn the disease, it learned to just identify hospitals. And it got pretty good performance measures. Also happened in COVID-19. So in this paper, they studied a classifier that was meant to identify COVID-19 from X-ray images of the chest. And instead of looking at the lungs, it basically looked at the borders of the images, and it learned to identify COVID-19 by looking at the contrast of colors in the images, which has nothing to do with COVID-19 itself, but the distribution of data meant that it was a very, very attractive shortcut. It could follow that shortcut and get very good results. Is this generalizable? Of course not. It has nothing to do with COVID-19. Perhaps you change the X-ray image and all of a sudden it no longer knows how to identify COVID-19. So this is very dangerous. And this all happens in text as well. So this is the Neven and Cow paper that I mentioned previously. And they were studying argument mining or argument reasoning here. And I'm not going to explain the task now because I will explain later, but all you need to know about this task right now is that there's a reason. So I hope that you see my cursor. There's a reason, there's a claim. So this is another section of the input. And then the model from the reason and the claim must choose the correct warrant. So it is given two warrants and it must choose the correct warrant. And what they noticed is that in the correct warrant, the presence of certain words such as not and is actually very much provided a strong signal that indicated that this is the correct choice. And of course, Bart, for example, took advantage of that and got a really good accuracy. When they balanced the data set according to these words, such that not no longer provided a strong signal, it came crashing down and it no longer could do argument reasoning. Now, why is this an issue? Why should you care? Well, an easy and very standard way to measure progress in machine learning overall, I would say, is through tasks. So you make tasks and you have data set for those tasks, and even you might even have competitions where you have a website with a competition on that task, and then different research teams can submit their scores and it will be listed there, and then this promotes competition, which means people will get interested in researching that task and they try to come up with better performing models. So it would mean like better performance means better models, which means more cognitive models, I guess. Well, I think it can be somewhat misleading. Perhaps the blind chase to solving tasks and winning competitions gives us kind of a tunnel vision. And it is possible that shortcut learning is happening in many NLP tests, which means that our progress in terms of the cognitive abilities of models could perhaps be much worse than what these competitions and the performances that we're getting in the tasks lead us to think. So the motivations and objectives for my dissertation and the paper, NLP has received, as I said previously, an increased interest in academia. So the rate of scientific publications have been skyrocketing, and the industry uptake has been really positive, with a lot of companies picking up natural language processing methods to solve all kinds of business problems. And improved state-of-the-art results are published very regularly, with models like the GPT-3 portrayed to be almost human-like in some respects by the media and enthusiasts. And people like to come up with different applications for it and kind of play around with it and talk with it. Research, however, is starting to show that despite these state-of-the-art results, in some cases it can be attributed to shortcut learning. And AI's long-term objective, which was laid out in the famous Dartmouth workshop in 1954, if I'm not mistaken, is to simulate any feature of human intelligence, right? So the objective in the research question becomes, how well do models generalize towards a core artificial intelligence task, which is common sense reasoning? And this common sense reasoning is naturally a very human capability. It becomes a good test of our cognitive abilities and our features of human intelligence. So is shortcut learning the leading factor for this, or do models effectively learn to do common sense reasoning, meaning they have good cognitive abilities? Okay, but first, before we even go into this, we need to define what is common sense reasoning, which is, again, actually not that easy to do, even though it has been an object of study for millennia now. Going back all the way to old Greece. But we can definitely say that common sense is an integral part of human experience. So it covers different dimensions such as spatial, physical, social, and many more. And it is knowledge that is shared amongst the community of humans. It can be global, like we, for example, look at the sky during the day and we see that it is blue. I hope that no one says otherwise, because we can literally look and see that it is blue. Or it may belong to a small community. For example, common sense regarding a dangerous animal that only exists in a small area somewhere on Earth, and for them it is common sense not to go near it. But for everyone else, they don't even have any idea what that animal is. And we use this knowledge to reach new conclusions, to justify our actions before others, and to generally understand how and why things happen through reasoning, for example. So chaining different knowledge that we possess in order to understand cause and effect of different events that happen in our lives, or to, again, persuade others towards something that we want from them. So it is a useful cognitive capacity to make sensible inferences and decisions, and it becomes fundamental in our daily lives. But it is not enough for the models to know these facts almost like memorizing them, almost like a student that memorizes knowledge before an exam or a test, but they must be able to reason with them, because it is not enough to just know that placing your hands in a fire will burn you, but also to realize that placing your hands in a fire will burn you because fire is hot and extreme heat burns our skin. So this is important because if we are to eventually have machines be deeply embedded within our society and do things for us, they need to possess this knowledge and reasoning capabilities in order to understand our worldview as humans, right? Our needs, our capabilities, our beliefs, and act according to that. Like a human chef would not want to serve us spoiled food, because despite still having precious proteins that we as humans do require to survive, spoiled food contains bacteria and fungi that makes us sick, and being sick is not desirable. No one likes that. And a machine or a model should know these things, such that yes, it has precious proteins that we require to survive, but if it did not know that we do not like being sick and that actually this kind of food makes us sick, then maybe it would serve it to us, and we don't want that. So the idea is to select common sense reasoning tasks. So we selected 4 of them, and then to select the most prominent models that there currently is for the transformer, or that currently was, because this was back in 2020. And then train them on it, and then devise a set of tests in order to understand whether shortcut learning is happening, or there is an absence of shortcut learning, and perhaps they really do, or they really are able to do common sense reasoning, which is a positive thing. This is good. So we need to select tasks, and we selected 4 of them. The first task is the argument reasoning comprehension task, which I previously mentioned in the Neven and Cal paper, which was the paper that kind of started this whole thing in NLP. So this is kind of argumentation theory, but destruction of an argument is usually defined as a series of premises that support a claim and conclusion. And there's actually a warrant, which is in itself is also a premise, that establishes the connection between the two, such that the claim and conclusion must logically follow from the premise. But warrants are oftentimes implicit on the supposition that it is shared knowledge between the parties involved. So naturally, this becomes an exercise that requires common sense. In this task, the model is given a reason, a claim, and 2 possible warrants, and it must select the correct warrant. The second task is the AI2 Reasoning challenge. So it is a multiple choice natural science question answering task. This would be like those types of exams and tests that we did, let's say in the 3rd or 4th or 5th grade with multiple choices. So it would be these kinds of tests. And actually this data set was made from a collection of questions from 3rd to 9th grade science exams. And it requires different types of common sense knowledge and reasoning, knowledge such as the experiments, algebraics, definition, and also different types of reasoning like analogies, algebraic, question logic, linguistic matching, and many others. So it's a very rich data set. And this is the type of thing that a model has to learn. So it is given a question, 4 possible answers, and it must select the correct answer. So for example, we see here, let's say in example 2, a telescope would be used for all the following, except to measure the density of Earth's atmosphere, to learn more about the stars and planets, and to observe the surface of the moon, or to better understand Earth. And what doesn't really make sense here? Well, to measure the density of the Earth's atmosphere. You're not going to use a telescope for that, or at least I hope that everyone here would say that. And for the third task, this is a very interesting one. It's the physical interaction question answering task. So it tests the capabilities of models to answer common sense questions regarding the physical world. And we humans, we find this to be very simple because, I mean, we interact with the physical world at every waking moment, right? We get up, we manipulate objects, we learn about their properties, and we've been doing this since we were babies. And we learn how to use them to solve problems, for example. But models, they lack this type of grounding, right? They cannot yet, at least. Maybe in the future they will. Well, that is embodied AI, but that's still very much new. But models cannot just get up and look grasp this bottle and see its properties. They must learn this from text, which is possible. You can describe everything with text, but it is much more difficult to grasp these concepts. So in this task, the model is given a goal and the solution to attain that goal. So it must choose the most sensible solutions. For example, here, example 1, what can I use to help filter water when I'm camping? You can use a water filtration system like a Brita pitcher, or you can use coffee filters. I mean, we're going camping, so we want to be light. We don't want to bring a Brita pitcher. So this seems like the most sensible solution, right? And the fourth and final task, it's very similar to the AI2 Reasoning challenge. It's a multiple choice question answering task. And as well, it needs different types of common sense knowledge and reasoning to be performed. It was built from ConceptNet, which is an ontology that tries to define common sense knowledge itself. So common sense concepts, how they relate to each other. And they took the ontology and the triplets for the ontology, and they gave it to Amazon Mechanical Turkers for them to generate questions and groups of answers to try to answer that question. And again, requires vast amount of knowledge types. Here's the task itself. So the model receives a question, 5 possible answers, and it must select the correct answer. So let's see here, example 1. What is something someone driving a car needs even to begin with? A, practice, B, feet, C, sight, D, keys, and E, open the car door. Well, certainly you need practice. You kind of need feet, even though, yes, maybe you can do without them. You need keys to open the door, and you kind of need to open the car door unless you can just go through materials. But definitely you need sight. I mean, if you don't have sight, I hope you're not driving somewhere. But so you definitely at least need sight. So now that we have defined the tasks, we need models. So what kind of models we're using? I've already given kind of a hint, which is transformer models. And here they are. So I'm not going to go too much into detail into how the transformer works. Assuming that people watching have some idea of how it works, but we can attempt to summarize quickly here. So it is an encoder-decoder model. The encoder encodes the input or the meaning of the input into a vectorial representation. It gives it to the decoder, and the decoder must then decode something. It can be text if we're generating text, or it can, for example, decode the correct answer. So it can, from A, B, C, and D, it can decode the correct answer. It just decodes something. So it maps a sequence to a sequence. It transforms a sequence to a sequence. That's why it's the transformer. And then in the literature, so this is how it was originally made. In the literature, they then started to separate both parts. So we saw in Bart and Roberta that they took the encoder and they applied it to classification tests in NLP, which gave great performance. It was great. And for this type of transformer, we pick Roberta as the model that we're going to use. And then also the decoder was separated and used in a type of architecture, which was famously the GPT series family of architectures, which only uses decoder. It's great for generating text, but also to do classification. And here we use the GPT-2 model. For the full transformer, so the encoder-decoder, we use T5, Bart, and Comet Bart, which is a neurosymbolic model. So it was trained on this common sense knowledge graph, which is Comet Atomic 2020, which encodes a vast amount of common sense knowledge with different types of different dimensions and types regarding just everyday experiences and events. And I hope that you can see this clearly. But for example, here we have someone who's getting their car repaired. What do they need before getting their car repaired? Well, you need a mechanic, of course, and the mechanic kind of wants money for it. And money is made of paper, which you can use to fold origami, and we can, of course, link everything together. And also event-centered, so what happens before you get your car repaired, where you kind of have to spend a fortune, unfortunately. And as a result, maybe we want to call you Uber for a ride because we're going to leave our car there. So it also has the social aspect of it. And how do you get the model to learn this? Well, this is Bart, which is the model Bart. And the common sense graph can be decomposed into triplets, where we have a head and tail concept, and there's a relation between the two, such as, for example, common sense can be used to prevent mistakes. And person X accepts person Y's apology. And how does person Y react? Well, he's happy because person X just accepted its apology. So we give the head in relation to Bart and make it generate the tail. So make it generate what would be an appropriate tail for that pair of head and relation. And through this exercise of predicting the tail, hopefully the common sense that is inside that common sense graph is learned by the model and is somehow encoded within its parameters. Okay, so we saw a lot of models here. And now that we have the tasks, we have the models, now we need to devise experiments to really verify whether, and this is trying to answer the research question, verify whether when they are learning common sense reasoning, these tasks that we saw, whether they are using shortcut learning or they're effectively understanding it. Even it's difficult to even define understanding, but whether they are understanding what they're doing, so understanding the task at hand. So in terms of experiments, the first experiment is just what we call the evaluation on common sense reasoning tasks. So we fine-tune the models on the tasks, and then we have a baseline performance to compare the stress test performance with. And now the experiments that I'm going to define now are all what we call stress tests. The first stress test is retraining and evaluating with partial input. And this is not too difficult to describe. So the tasks we saw, for example, had different segments of the input. So we have, for example, questions and possible answers. And we have the reason and the claim and the warrants. And we have a goal and solutions to attain that goal. So we can kind of separate the different segments of the input. So now if we made a data set, for example, where it only has the possible answers, but it does not have the questions, and we made the model learn from this data set and test on this data set, it would be expected that it could not perform this task, right? Because, I mean, it has the answers, but what is the question? What question is it answering to? So it should be random. It should be a random baseline, because unless it can really tell what the question would probably be just from these answers, it's not expected for them to learn it. Or, for example, to do argument reasoning, I mean, if you don't have the claim or the reason, what kind of reasoning are you doing? So removing certain parts of the input, making a new data set from that and giving it to the models. And if they are able to learn the task, then it means that they don't even need the whole input in order to perform that task, which means then what kind of task are you performing? What are you actually learning? Because it is definitely not the task that we meant you to learn. The third one is an adversarial attack. This is somewhat similar to the previous experiment, even though it's a bit different. So in this one, we have a model that has already been trained. And what we're going to do is we're going to change the test set minimally, so minimal superficial changes, such as, for example, changing a word with its synonym, such that the model switches its prediction. So let's say it is saying that answer A is the correct one. We're going to change like one word, for example, by its synonym, and maybe instead of saying A, all of a sudden it says that the correct answer is B. And it should not be doing this because the semantics are the same, yet because we changed its form, all of a sudden the model cannot do this task and say, oh no, this does not make sense to me anymore. It's now B, the correct answer. And this should not be happening. This is not a good thing. The fourth experiment is the data contamination, which has been a serious problem in NLP now. So the methodology for NLP has been, we gather a lot of text from the web. So we scour the web, we scrape the web and get a lot of text from different websites and different blogs. And then we pre-train using language modeling. We pre-train the networks and then use that network to perform NLP tasks. But now the problem is, so we got a lot of data, a lot of text from the web. What if when we're building data sets for tasks, we are accessing the same websites that were already scraped and used for pre-training. Now it means that, for example, the test set of that data set that we assume the model has never seen, because we want the test set to be something it has never seen, though such that we can test its generalization power. Things that are present in the test set actually have already been seen by the model. So it saw it during pre-training, and perhaps it memorized it, which means that it can then use it to get a good performance in the test set. And this is not desirable, because then we don't know whether it has generalization power to unseen data, and then we release it to the wild, and all of a sudden it cannot do the thing that we wanted it to because it did not understand it correctly. The fifth experiment is the cross-task evaluation, which is basically taking a model that was trained in one task and then testing it on every other task in a zero-shot manner to see the generalization power. And sixth, it's just searching for shortcuts. So we search for two shortcuts: the class imbalance, which if the classes are imbalanced, then yeah, the models can take advantage of this, of course. And then lexical cues, which is the thing from the Neven and Cal paper that we mentioned, like, for example, the word not having a really good, being a really strong signal for a certain class. So these are what we call lexical cues. So now I'm going to give you the results, and we're going to discuss a bit about the results, but this will be a lot of tables, so I hope that you do not get bored, but the most important things are always in the text, so you don't even need to look much into the tables. Everything will be in text, and that's what you need to focus on, because these were a lot of results, but each result brings an important thing for the narrative and for what we can learn from them. So the first experiment is the evaluation, of course. We fine-tune the models on the tasks. And what can we learn from this table? These results are in accuracy, by the way. We can definitely say that Roberta stands out. It obtains the best accuracy in 2 out of the 4 tasks, which you see here in bold. A new state-of-the-art is reached for argument reasoning comprehension task, although this was not the goal, because we are just looking to actually try to understand what the model is doing. We did not mean to obtain the state-of-the-art. And Comet-Bart provides an advantage. Comet-Bart, which is the neurosymbolic model, provides an advantage over the baseline, which is Bart large, even though it is not statistically significant, but performs below Roberta. So Roberta, even without having these refined priors using the common sense knowledge graph, is actually able to perform better than Comet-Bart. Now, after we did this experiment, we decided to carry on with the stress tests with only 2 of the models because of computational power that is needed to do these experiments. And we decided to carry on with Roberta Large, which was our best performing model, and Comet-Bart, which is the neurosymbolic model, because we still had that hint that perhaps the refined priors would give it a bit of an edge, and maybe it wouldn't have to rely on shortcut learning to perform these tasks. Okay, so the first stress test is the retraining and evaluation partial input. And from this experiment alone, we could get a lot of conclusions, and it was a really good set of results that we got, and we got really excited. So let me just briefly, I told you that you didn't have to look at the tables, but let me just briefly explain what is in these tables. So here's the full inputs for each experiment. So each data set, so argument reasoning comprehension task, AI2 reasoning challenge, physical interaction Q&A, and common sense Q&A. Here's the full inputs that they have. Here's the best scores that we obtained in the last experiment. So for Roberta Large, which has a diamond, and for Comet-Bart, which has a square. And there's a partial input. So basically this means that we trained a new model with just the claim and the reason without the warrant, the reason and the warrant, so without the claim and the warrant, so without the reasoning. And you can see that with just the claim and the reasoning and the warrant, it is able to obtain very good accuracy scores, almost the same as when using the whole inputs, which means that this data set is still broken despite the revision that was done in the Neven and Cow paper, and it only really needs to look at the claim and the warrant to obtain an excellent score, which means it's not really doing argument reasoning, because you need the 3 sections to do argument reasoning. The AI2 reasoning challenge, it seemed normal for Roberta Large, as you can see here. It's below random baseline even, but Bart was able to perform well on it by using a data set that only has the answers. So think about this. The model is able to give good answers, correct answers, to questions it has no idea about. It's the same as a professor giving you a test with just the answers and expecting you to know the questions that these answers belong to, and you picking the correct answer. But yet the model can do this above the random baseline. Physical interaction Q&A is also the same story. It is equally broken. It is giving good solutions. So here's the data set with only the solutions, and it is able to get very good accuracy scores, almost the same as using the whole data set. So it gives great solutions to goals it has not seen. So it has no idea what the goal is, yet it is giving great solutions. And Common Sense QA, interestingly, seems to be resistant to this. So only this, which is marginally above the random baseline, we do not even consider this to be like a score indicative of anything. It seems to be more resistant to this phenomenon. So we got really good things from this. So we learned that argument reasoning comprehension task, AI2 reasoning challenge, and physical interaction Q&A seem to be broken, and the models don't need to actually know the task that we meant them to, but they seem to find things in the data that they can use to get good scores. So the adversarial training, this is just a brief description as to how the algorithm works, which is from the Jin et al. Paper 2020, which is a method called text fooler. And in text fooler, it uses word embeddings, glove word embeddings, to just measure the similarity between words. So first, let's say we have a Bart, and we give it this input text, and the Bart says negative. First, text fooler finds the most important words for Bart to have chosen this as negative, and it said that contrived, situations, and totally are the most important words. Then it's going to try to find similar words that do not change the semantics of the text, and in here it found engineered, circumstances, and fully, which, yeah, it does not change the semantics. And all of a sudden, the Bart, instead of saying, oh, this is negative, it says, this is positive. This should not be happening. The semantics doesn't change. It's just a change of words. If it really understood the task, this should not be happening. And this is an example that happened in one of our tasks. So we have a question here. This is from the AI2 Reasoning Challenge. We have a big question here. We're not even going to read this, but we have a big question here. And in the choice A, the word ability was changed to capacity. And before, the model predicted B as the correct choice, which is right. It is correct. And by changing just this word from ability to capacity, all of a sudden, the model says that A is the correct answer. The semantics do not change. It should not have done that, yet it does. So the results for each task, as you can see here, well, we use text fooler, of course. And as you can see here, both Roberta and Bart show a lot of brittleness when faced with these adversarial attacks. The deltas are absolutely huge, and these are in terms of accuracy, with even 0.5 accuracy down in physical interaction Q&A. And a sharper drop is actually seen in the tests that were flagged in the previous experiment for being broken. So the argument reasoning comprehension task, the AI2 reasoning challenge, and the physical interaction Q&A task, which is an interesting pattern. For data contamination, we saw the overlap, n-gram overlap between the test sets for each task and the pre-training data set for Roberta and Bart Large. And this was based on the methodology from GPT-3. We can see that argument reasoning comprehension task is entirely clean, And then there's different levels of contamination for the other tasks. And then we kind of separated the test sets, and we produced a dirty set composed of just dirty examples, and then a clean set composed of just clean examples. And we saw that data contamination did not have a negligible impact, and as such, it should not be a factor. Memorization should not be a factor and that could explain the results that we have been obtaining in the previous stress tests. Now we're almost finishing up here, so bear along with me. In the cross-task evaluation, the things that we can really uncover from this is that Common Sense QA provides best generalization, which is actually interesting because it is the least affected task from the previous experiments, which could mean that not being prone to shortcut learning leads to more generalization, and this could actually be an indication of very good data quality. And then the only one that went below random baseline is a model that was trained on physical interaction Q&A and then tested on AI2 Reasoning Challenge went below random baseline, both tests being broken. And then argument reasoning comprehension task was the weakest contributor, with providing very low scores or very low generalization power for the other tasks. Okay, last result, and then we go for conclusions. For shortcut exploration, class imbalance could not explain the results. So there was a slight imbalance, but it cannot explain these results. And no strong contiguous lexical cues were found. I say contiguous because we tested unigrams and bigrams, and actually this methodology only considered n-grams, but it could just be that there's lexical cues that are nonlinear, like having this word in position 2 and that word in position 44 somehow makes it that it is related to the correct answer. So this could be happening, but we did not test on that because it's really not that trivial. But we saw that in these tables you can see in the paper, so I'm not going to go too much over them, but we found some cues, but they were not productive, so they could not explain the results that we got. So conclusions. Models do better than expected without all the input segments. This should not be happening. This is really indicative that the shortcut, that the models perhaps are using shortcuts to perform the task and really not doing the task how we meant them to, which is a very tricky thing. Models appear to be very brittle when adversarial attacked, which seems to come from this very surface level understanding or learning of the tasks. And then Common Sense QA, which is the least affected task, generalizes better to other tasks, which is what we saw in the cross-task experiment. Data contamination tests show that memorization is not the explanation factor. And we performed a few tests to investigate whether two possible shortcuts were the explanation factor or the explaining factor, and they were not. So we did not find the major explaining factor or the major shortcut, but we did find hints that shortcut learning is happening. And it is also then a hint of the low cognitive capabilities of these models, and as such an indicative that perhaps we lag a bit behind on AI's long-term objective. So what now? What can we learn from this? I think personally that maybe a careful review of dataset development methods. We saw that data quality, Common Sense QA, was not affected by this. So data quality definitely has something to do with this. So careful review of dataset development methods and even learning methods, how we can learn more efficiently and not be stuck with shortcut learning. And then, does this happen in challenges overall or in data sets overall? So it would be a problem if so. So this is something that also should be up for review. So where does this happen? Where can we spot this happening? And perhaps less infatuation with metrics, so pursuing performance metrics, and more infatuation perhaps with comprehension. So maybe just stacking layers on top of each other and making the accuracy or the F1 or whatever metric go up. Maybe this is not the way, and we should be more infatuated with actual comprehension of these tasks and how the models are actually learning the tasks. So perhaps this is what I think can be extracted from this. So thank you so much for watching, for listening. If you have any questions, you can leave them in the chat. This is my email if you want to talk a bit more about this, or if you have any other questions. All the code and data are available at this link. And here's my my page, whether if you want to find out a bit more about me or you want to contact me. If you forget this email is there too. Always open for discussions and collaborations. Thank you.
Thank you so much, Ruben. I think that everyone agrees that it was a great presentation. Let's switch a little bit more for questions to arrive in the YouTube chat. But okay, I'll just whenever, yeah, if we need your screen, we'll share it again later. Let me just pick here a question from Inish, which I think is very interesting. So do you think these findings suggest that instead of evaluating models with a single metric like accuracy, we should have other metrics that balance accuracy, shortcutting, or whatever, how you call a metric that measures that, adversarial examples and biases? So what do you think about this?
Definitely. I think perhaps focusing on just a single metric, perhaps it is a bit more, it contributes to the problem. And definitely finding out metrics that account for this shortcutting and even implementing them in the training process would be a really cool thing to do in terms of research. And it could be the way forward. And perhaps adversarial training is also a thing. So that is already a research path. So adversarial training, and it does seem to help. So yeah, definitely, I think so.
Yeah. So, but do you think this can only be? So, do you think you can also like have a loss for this, or just like a metric?
Yeah, you could incorporate it into a loss. I don't see why not. So you can incorporate any metric into a loss. So yeah, I think you can definitely. It's not just about the input that gets put into the model. So adversarial training, you perform adversarial attacks in the input and you give it to the model. But I think it could also be incorporated into the loss, such that when you back propagate it into the network, it is more knowledgeable of these types of biases.
Yeah, that makes sense. But sometimes, I don't know, it's not so. Normally people just go back to like a regular loss and then evaluate with different metrics. But yeah, they normally stick with just a custom loss. So that's why I was asking if you think that's wise or not. So let me just move into Luis' question right now. So how does shortcuts relate to causality? Is it fair to say that shortcuts are ungrounded biases or associations lacking causality?
I think both could be at play here. So associations lacking causality, definitely. So we saw that in the paper by Neven and Cow. We did not find such associations in the data sets that we explored, but we saw it definitely in the Neven and Cow and in some other papers that have been released. And also ungrounded bias. This is like a grounding has been a regular conversation that we had during my thesis and even before. And I think we reached the conclusion that it is really important. And some of these biases may come from lack of grounding. And grounding, I think, has been, a new area of focus in NLP and in general in deep learning. So it seems like people are starting to really take a look at this.
Yeah. So I have one question regarding the adversarial attacks. Did you have a chance to look at the attention maps? Like, how did the attention maps change with the attacks? Because that could be interesting to see, like whether the maps were actually remaining on the same words or whether they were changing, because that can also help us interpret why they are the models are failing with the attacks.
Yeah, definitely. I did not have a look at them, but I would posit that yes, the attention maps could and should shift, and it's actually a very cool idea because you could incorporate this in a way into the loss function. So maybe there's certain patterns in the way that it shifts, and that could then, when it is observed, when you're training, maybe that could be incorporated into the loss function, be some useful information for the model.
But we should expect that them not to change, right? If the attack is, and we aim to change the word to a synonym, it should remain the same. So that's
exactly. But I think it would change if the model is really susceptible to these adversarial attacks. I think that's what we would actually see, because we saw that the models were very susceptible to this, which means that the attention maps and maybe the gradient maps are changing, or the saliency maps are changing, which means that, okay, this is a bad thing. It should not be doing this.
Yeah.
And it's precious information that could potentially be used.
And also related to this, we have here a question: how does this work relate to explainability?
So it relates to, I think it's well within explainability. So it has a bit of just a general application where we apply the models, but then we're trying to show that these models are not really, I would say, it's difficult to use the word understanding, because even for humans, defining what understanding is pretty difficult, but I'm going to allow myself to use this, whether the models are understanding the task at hand. And so, yeah, it relates to the works of explainability, although I don't think it provides too many answers. So it provides hints, but it doesn't provide too many answers, like, for example, saliency maps or attention maps could uncover. But I think it's still an important problem, shortcut learning, and it is not so trivial to catch them doing it.
Okay, so I think I'll pick one more question because we are not having different people asking. So I'll pick one more from Inish. Your work showed some problems in widely used NLP models. What are some directions we can take to mitigate these problems? I think this is a good question to maybe end the session. So what do you think about this?
It's a tough question. I thought a lot about this when I was finishing up my master's thesis. Like, we've shown that there's problems here, and I mean, what can you do, really? And from the discussions that I had, a lot of it has to do with data quality. What is the solution for this? It's difficult to tell, really. Difficult to tell how these why, for example, Common Sense QA was the data set that did not show any type of shortcut learning. So why would that be? So personally, no clue as to why that type of way to generate data sets was better than the others. But definitely data quality, we have to look more at the data and less be so focused on perhaps scaling the models. But then the models themselves, like any machine learning classifier, what they want to do is just minimize the loss or maximize some metrics. So they will, whatever they can find in their representation or the features, they will use it. If there's an advantage to them, then they will use it, whether it's a generalizable feature or not, because it's within the distribution of the data in the training set. So they will use whatever feature is useful for them. And in order to generate useful features and make them actually pick features that are generalizable, I would say that it relates to what we were talking about. So it relates to, for example, adversarial training. It relates to making sure or devising loss functions that incorporate more knowledge, such that this does not happen. It relates to putting inputs that are more informative and perhaps not just language, that are more informative. So multimodality, for example, or types of grounding that are more informative, such that the models do not just fixate on certain patterns in the data that are not generalizable. So there's basically two directions that I'm talking about here. It's the modeling and the data. Data is very important. We saw that. And the quality of data, we have to review the methods, like I said, and also the models, the way models learn. We know that they are going to pick whatever set of features that are important to maximize or minimize the loss. So we have to provide them a way such that they do not just rely on them and they actually generalize. So not too specific answer. I cannot cannot tell you what the golden secret is. If I had, I would have published already and perhaps have a very good paper. But yeah, it is somewhat around that.
No, but I think that's a great answer. I also agree with that. We have two different kinds of problems that we need to solve: the data problem and also the algorithm, the methodology problem. So, but I think maybe fixing the data sets, it's a little bit easier than solving the way that we can help the models to generalize better. So, also, Luis posted here a question, and I think we can answer him. Mm-hmm. So, aren't these kinds of biases common in human reasoning too? If so, can we really assume that common sense reasoning comes from removing shortcuts?
That is a great question. There's actually this in my dissertation. I had a look at a book on learning maths. So it was from high school, how to teach high school and before high school, so basic school, how to make them learn maths. And one of the problems that they had is, for example, in multiple choice questions, sometimes students don't really go into a full deep understanding of the question. They just kind of almost pick randomly when they don't know, which is normal, but they try to spot like certain patterns and then they answer the question without really comprehending what is going on. So yes, even for common sense reasoning and any other type of knowledge, sometimes we have these biases. So yes, we do have these biases in human reasoning, although I would say that we can go above that. So in the example that I gave from the adversarial training, changing one word to the other, we as humans, we would not change our answer. It's very obvious which correct answer, which correct choice it is. And if we see, for example, the teacher changing one word with a synonym, we would not fall for that kind of trick. Yet the models do fall for that kind of trick. So yes, human reasoning is flawed. We know this. There's a lot of books that cover this. Psychology studies this. Yet these types of shortcuts that the models take are, I would say, much more shallow than that. They're not that deep like the type of flaws in reasoning that we commit. And whether reasoning comes from removing these shortcuts, I would say that no, but it helps. So for example, common sense QA, we did not find any shortcuts. The models can perform well, and can we say that they actually comprehend common sense reasoning and it performs well on the task? Well, that is a great question. I really don't know. I'm biased to say no, but I mean, it's still up in the air. But it is the way to go. You have to remove the shortcuts so that you are at least safer in saying that the models can do common sense reasoning, can perform this task.
Yeah. So could you just provide the name of the book just for us to before you know?
I would have to go into my dissertation. I can't remember the
okay.
book, but if there's like any way I can provide you after the presentation, yes, I will provide.
We'll post it on the with the notes of the presentation. We can provide it, for people to look into.
Okay, yeah, perfect. Then I'll give it to you.
Okay, so thank you very much, Ruben, again for the talk. I think it was a great talk, and it was certainly a pleasure for me to host it. I hope we can have a future talk once more, and for anyone who is interested in our sessions, you can also provide feedback with our forums that we have on the YouTube chats. And if you want to suggest any new speaker, please do. We will greatly appreciate it. And so see you next time for our next meetup. Bye, Ruben.
Bye. Thank you.